All right. So I think we're good. All right. Those of you on Zoom, you can hear me all right. Is that right? Can you hear me okay?
Yes, that's fine.
Okay. So don't let me forget, we can only work on this one board. So just stay frosty if I start getting in the habit of going over the other board. All right. So apologies. I got to be over whatever. All right. So our goal is to talk about Ampere's law. So I'm going to first bring up our old friend, Gauss's law. And again, in the notes in the workbook, I'm on page 163.
Yes, that's fine.
Okay. What's that? Oh. Stay frosty if I start getting in the habit of it. All right, whatever. Okay, Gauss's law. So Gauss's law, you probably remember, was something like that. And then in practice, didn't we almost always just change this to EA? And I'm going to color that red for a second. Was equal to 1 over epsilon naught. The most general way to get Q enclosed, we sometimes had to do an integral. You remember that? There's an integral of rho dV. And a lot of these problems, it was, what's the area I need, what's the rho, and what's the dV? So these the colored parts here are the ones that were kind of the nuts and bolts of this. And to give you an image here, I'm going to start with a cylinder. Okay? So remember when we did that, and let's say the tricky part, was it outside or was it inside? Which was harder for Gauss's law? Yeah, when your Gaussian surface was inside. And do you remember we'd sometimes say, oh, there's some radius, little r, which is different than the outer radius, big R. And then we would slice this into chunks. Whoops, that's pretty sloppy. And this had some last radius. I think I called it R twiddle. Remember all that? Sorry, it's so tiny. Can you even read that? Are you guys good? Okay. All right. So, all right, this was kind of our warm-up. Well, we could go through Ampere's law and drive it, and we will in a minute, but I'd rather focus on the similarities for a second. So Ampere's law is very similar. Instead of an integral of E dot dA, we're going to do an integral of B dot ds. Oops. All right, and that's going to equal some constant times current enclosed. All right, so previously we used to do charge enclosed, and we could figure out that from density. What's the equivalent equation we could use for figuring out current enclosed as an integral? Does anybody remember? What was the type of density? So this was charge density. What's the type of density if we're figuring out current? What was the symbol? J. And then what do I need to integrate to make the units right? The area. To be clear, I think this helps. If uniform, you know what I mean? If I just say if uni, I mean uniform. Oh, what the heck? Let's write it. If uniform, J was defined as current over area total. Remember that? Or total current over total area. Does that sound vaguely familiar from some class a week or two ago? All right, sort of like over here. Remember, if this was uniform, rho was something like Q total over volume total. Does that sound maybe more familiar? The idea was, if you have a uniform density, you could plug that in there. If you have a uniform current density, we could plug this in here. Same kind of thing. All right. Well, what would this side go to if you had to guess? This went to EA. BS. You can call me on that BS right there. That's legit right there. Right? And the idea is, what does this S mean? Well, what shape are most wires? Cylindrical, right? So that's why I'm focusing on cylinders here. We know that there's some radius all the way out to the edge. I would call that big R. There's some Amperian loop that has a radius little r, and we could build this thing up out of these slices like this that has some radius r twiddle. It's like some really bad industry logo. RRR. Shredded wheat. Okay. Anyways, it's the same idea as this picture, right? So the tricky part in all these problems is basically figuring out your R's and figuring out your symbols. Now, when we were doing Gauss's law, remind me of some of the ways I tried to trick you in Gauss's law. Any of them? There were a lot, right? Or what were the variations we did on Gauss's law problems? You could do sphere and cylinders. How many spherical wires have you seen in your life? Not many. Only on that last test practice, right? But we generally are going to avoid spheres. So one cool thing about Ampere's law is we're going to focus on cylinders. What about slabs? You could have a slab of current. And that's basically, imagine you take, imagine you had a cylinder here, right? And then you put a thin layer of metal on top. And you could have current flow just in the surface. We're not going to focus on that in this class. Could you do it? Yes. So could there possibly be applications of spheres or slabs? You bet. But they're not on the test. Okay? So basically, we have 3 times less geometry to learn. Sweet. Okay, what's another thing that I used to mess with you on Gauss's law? Conductor versus insulator. Let me ask you something. Can air conduct electricity? Does lightning exist? Yes. Yes. Everything can be thought of as a conductor from an Ampere's law standpoint. What's different is current flow is just more or less difficult. So we don't have to worry about the distinction between conductors and insulators anymore because everything's going to conduct electricity if you just apply enough voltage. You put 3 million volts on something, you can get, right? If you apply 3 million volts to a meter of air, 3 million volts over this distance, you'll get a spark. Okay, you can make it work. So we don't have to worry about conductors and insulators. What else? Let me put cylinder here. What else? Uniform, non-uniform, right? That could still be valid. You can have a non-uniform, but remember, non-uniform is not that bad. It's just plug in some weird equation, right? And then what's the last? Shells. Multiple shells. That is obviously something we're going to do. The cable I was just looking at from that TV that's not working right now up to here uses a coax cable. We're going to be studying these. What was the practical application? Do you remember what we used Gauss's law for? We said, okay, we did all this Gauss's law, but we actually used it to discuss something that's a physical object in the real world. You studied it for your last test, chapter 25. Capacitors. Remember we, in theory, used Gauss's law to understand capacitance? Similarly, you could, in theory, use Ampere's law to understand inductance, which is a different property of electronic circuit components. So there's an application to this. Great. Let's remind ourselves of the idiosyncrasies here. I think it's important here. When we talk about this area, when we were over here in Gauss's law, what was the area for a cylinder? that we oftentimes use. 2 pi r L, right? What was dV for a cylinder? Area times thickness. And then we call these R twiddles. Remember that? So that was our kind of our Gauss's law. So now I guess we better understand the 2 new pieces. These were the hard parts, right? Constantly figuring out what am I supposed to do in this problem? Okay, let's look at this one. J is the current density. Fine. What does, well, let's start with S. What are the units here? What does S normally mean? Meters. It must have something to do with this red dotted line. What do you think S means? Perimeter. So we could call this S equals 2 pi r. It's the arc length all the way around. It's the length of the loop. So over here, if you remember, this was the Gaussian surface area, right? This is going to be called the Amperian perimeter, so to speak. Right? Over here, this was a Gaussian surface. This thing is called an Amperian loop. Just if you're trying to read the terms, okay, got it. So far, so good? All right, we got one more piece to fill in. It's this dA, right? We see there's quite a lot of similarities, but these are some important distinctions. What is dA? What does that mean? It's the cross-sectional area of your slice. Okay, this is where it gets confusing. So let's focus. Okay, hear me out. I want to see how much current is enclosed inside this red loop, right? So what I want to do is I want to figure it out. Think about these. Each little piece here, if you combine these, each little one should give me a small amount of current. The idea is the total current enclosed is equal to the sum of all the little bits of current. Now, this J, it has to do with the cross-sectional area. So think about this. I'm trying to build up this circle out of all these slices. What is the area of this slice? Said another way, if I was painting this board and you put some green paint there or green ink or however you want to call it, what is the actual surface area of green ink that I used? Just the ink for this one little bit, right? Because do you agree I could keep adding more and more of these and fill in the entire thing with little circles like that? Money. 2 pi r twiddle, that's all the way around, times dr twiddle. Excellent. And the idea is, okay, that's the area of this piece of green paint. Then I can put another piece of green paint and just keep building this entire area out of all these circles of green paint and eventually get there. Can you see this at all, Jess, or not?
I can see it, yeah.
All right. I know you can't get the green and red, but yeah, there's a...
I said R to a little R. So.
Yeah, you got the symbols to go for it. So, all right. Okay. Now you know why I have to do these R twiddles, right? It's important to distinguish the different radii. And yeah, so this is one. All right, enough on that. It's important that they have different symbols mathematically because they are not the same. All right. Okay. Well, at this point, well, there was kind of one other annoying thing whenever you're doing these problems. Let's figure out the limits, right? If we were doing this particular problem here, let's go back to the Gauss's law. What would my limits be for this particular problem? I want the charge enclosed by the red loop. What would my limits be? 0 to what? Little r. Yep. Well, over here, what do you think my limits would be? 0 to little r. You feel like you know Ampere's law? Should we call it a day and go to the bar?
All right, let's go.
Okay, you're buying. But so I know I tortured you guys at the beginning of the semester. This is supposed to be your reward. I'm hoping this is easier to understand than Gauss's law was because you suffered, right? This stuff is very tricky. We need to do examples, but I want to leave that up there in case anybody has questions. Any questions about any of this? Or is there anything that jumps out of your mind as you're thinking about the analogy is pretty close. Notice everything is stepped down one dimension. So we went from an area to a length. We went from a volume to an area. Whatever. Okay. This was called electric flux. This is not called magnetic flux. It's not that part is not the same, right? So there are some differences. We will discuss magnetic flux at the end, and it's probably one of the most important things to understand in electrical power generation. So we'll talk about that. Let me see if there's anything I want to talk about. Let's get to work. Should we do the simple first problem? Let's go to 29.23, page 164. Zoomers, any questions from you? You got it all right?
Yeah, I'm good.
Okay.
Doing good.
Gonna see if I get lucky here. No, still nothing. All right. I need to erase. I'm going for it. So what problem did I just say? 29.23. Start doing it. I'll catch up. It's basically finishing the example that we just started here. You guys actually notice the difference when I use this cloth or not? Does it help? Like keeping the board extra clean or not? Yes. Yeah. All right. All right. Okay, we've got our Amperian loop. Just maybe follow along for a split second. We're not going to do this every time. Just watch what I do here for a sec, everybody. The current in this wire, we are told the current is running out of the page. Okay, so the current is running out of the page. Right here at this point, which way is the B field? Right here. This is a long skinny wire, is it not? Where's my meter stick? Where is it? No. Well, this is a long skinny wire. We're looking at a cross section of the wire. Do you agree? This wire extends outwards to infinity and inwards to infinity. If I'm trying to figure out the direction of the B field at one particular point, what do? Line my thumb up over here. Which direction is the B field? Oh, yeah, or J hat. Good. How about up here at the top? Yep. And you see it kind of circling around in the pattern that we saw the other day with the compasses? You know what I'm talking about? And then down at the bottom, I'm just going to draw 4 of them. That's enough. What should be true about the size of the magnetic field everywhere? Shouldn't it be the same if I'm equidistant from the wire? All right, if it helps, you probably recall B was mu naught I over 2 pi A or something like that, where A was the distance along from the wire along the perpendicular bisector. But if it's an infinitely long wire, any distance away A would be along the perpendicular bisector. All right, but if you're saying distance, same magnitude, agreed? Okay. Now, if you want to go around this loop, right, we want to do what's called a line integral. So I need to go around in some direction. There's two logical directions. I could either go this way or that way around the loop, right? So I could either go clockwise or counterclockwise. Which way do you think would be nicest? Should I go around this loop clockwise or counterclockwise? Which seems pleasant?
Counterclockwise.
Counterclockwise. Not only is it the standard math direction, but the B field points the same way. Well, isn't this a small amount of length as I go around the loop? Sorry, I can't draw it perfectly here. But the idea is, right here, a small amount of loop would go this way, small. So far, so good? Well, I'm only showing you this for one reason. If we go all the way around the loop of B dot ds, humor me. What should be true about the dot product here? You're going to get cosine of 0. That's 1. How about up here? So doesn't this go to B ds without the vectors? You know what I'm saying? That's all I'm trying to say right now. The idea is, aha, if I have a cylindrical wire and I use a circular loop, I get this interesting thing happening where the dot product drops out. Huh, well, wait a minute. What's true about the value of B, right? The magnitude of it is, so what can I do with this? Pop it out. Well, wait a minute, what's the integral of ds? S. So this becomes Bs. If you were curious how to get from this integral to this, now you know. Do you ever need to show me that again or talk about it ever again the rest of your life? No. But if you wanted to know how, I find it interesting. So I feel like we've covered that. We checked that box. Everybody cool with that? So from now on, you're probably going to start right here and not waste your time with that. The point of this is you really need to think about, we will come back to this, I think, once, and I'll discuss it later. There's one other problem I think it shows up. So let's worry about it then. Okay. So this is equal to mu naught I enclosed. Right? Okay, well, how much I is enclosed? All of it. So doesn't this become B S equals mu naught, some constant, just I, the current. But again, remind me, what is S? The perimeter. So in this case, what is the perimeter? Which are? Solar. Exactly. So the red loop tells you which radius you use. So this is always going to be your little r radius. Just like in Gauss's law, it was always your little r. All right? And then I think we can agree, I can move this stuff around. I should start making ASMR videos of just cap removal and placement. It's like, somebody would probably watch that. Yeah. That's my new get rich quick scheme. I got to figure out a way to make an NFT out of that. All right. Oh, this cap is so well removed. Anyways, this should not surprise anyone, right? Now you might be saying, this is totally stupid. We just derived this result. It's kind of a circular reference. Well, in a lot of ways, yes. But I do want to point out one thing here. Or two things. Number one is we have just shown, do you agree the radius of the wire doesn't matter? So what we have shown is, okay, we assumed this was true previously, that the B field near a wire was this number and it didn't depend on the radius of the wire. And now we've kind of demonstrated that is shown to be true here. The other thing was, when we did Gauss's law, we could not only understand the magnetic electric field outside, but the electric field inside. The same will be true now. We can take this understanding in practice and bring it inside, and that's something that we didn't understand. How to analyze the magnetic field inside of the wires. All right. So that's kind of cool. Is this all there was to know about that? Yeah, pretty much. All right, you ready to do the next case? All right, any questions about this? All right, so maybe I'll make a note here. For R greater than R, B was equal to mu naught I over 2 pi R, and that's the magnitude of it. I'm just going to keep that hanging around. That was case one. All right. You know what? I just got to start over. Okay. I'm going to draw the same circle now. We're going to case two. We're going inside. All right. So we've already sketched this out in on the first board I did today. Let's see if we can remind ourselves of how we did all that. There's a little radius R. There's this radius out to the outside. We call that capital R. And then we need to slice this thing up, right? And this had some radius R twiddle. Is that visible in the back? Okay, thanks. Okay. Caps are coming off. We'll have a good time now. Here we go. Let's see how much I write on myself. B S equals mu naught I enclosed. That's Ampere's law. Whoops. That's Ampere's law. In this case, we could plug in that this is 2 pi R, but let's save that till the end. Generally speaking, I don't want to have to write any more than possible, or I want to write as little as possible. So let's just keep that BS floating around. What am I going to start attacking? Which part of this? I enclosed. What should I write for I enclosed? The sum of all the DIs, or JDA. Right? What are the limits? No? Yeah, look, because we're not enclosing all of it now. We're in case two where it's inside. We only want to go 0 to little r. Is this uniform? Did it say it was uniform? I think it said. Yeah. Thank you. Okay. What does that sentence tell us that I can do? How does this help out? I total over area total. Remind me, was this the sidewall area? Cross-sectional. This is crucial. That's cross-sectional. Okay, well, I'm going to reach out. I'm going to assume that the total current is I. What's the area total I should use? Pi big R squared. Got it? Think about it. If I have this current spread out over the whole thing. That's why I have to use big R for J, right? It's the total current over the total area of the entire thing. So far, so good? What was dA? Remind me? It was the area of this green line, not the area that it encloses. It's the area of the line itself, right? Because remember, we're going to build up this entire red area out of these little green slices and make them thicker. And yeah. You're good to go, right? Okay, see you at the end. Is J a constant or not in this case? It's uniform. It just pops right out. So then there's basically a bunch of stuff you can pull out of the integral. Let's do that real quick. You got I pull out a 2 pi, do you see? I'm going to pull that 2 pi out. And then I'm going to integrate like that. Make sure I didn't screw that up. Is that right? U naught, I got the J. This is the J. This is the 2 pi. Yeah, I think that's it. Oh, I forgot my limits. All right. Now, you might be saying, dude, why aren't you canceling stuff? Just from experience, I just want to hang on a minute. Just, yeah, give me some latitude. Normally, we would cancel a lot of stuff. I just want to show you some stuff that happens. You probably have your own style that you like to do from doing Gauss's law all the time, right? You know what works for you better than I do. All right, like that, right? Now, a lot of you might be saying, well, wait a minute, I know I'm going to get a 2 pi r here. Why don't I use this 2 pi to cancel that 2 pi? Well, look at this. Do you see I get this 2 pi canceling this 2 pi? And so a lot of times when you're doing this, I like to kind of leave this side alone until after you do the integration. Remember when we did that in Gauss's law? I was like, just don't mess with this side until you plug in the limits on the other side. That was my recommendation. It's not that you can't be clever, but now I see that, okay, because both terms, when I plug in the limits, would have that 2 in there, so I can get rid of that. And now what do I get? I think this one has an R squared, like that. And I'm going to go ahead and write this result up here a little bit easier. I guess now, I should pause. Everybody okay with it? And then now what I'm going to do is I'm going to go back to this and I say, wait, isn't that a 2 pi r? Like this? Because that was the distance all the way around the loop. Remember, S means distance around our Amperian perimeter. So in this case, I'm going to rearrange this and just see what you think. I claim it makes this result. And I'm going to write it maybe in a different way than you might. Okay. Take a second, make sure you believe that flips around. Is everybody cool with this format? Why am I doing this? You remember when we were doing Gauss's law? Almost all of them had this form of KQ over R squared times some other stuff, or 2K lambda over R times some other stuff. We see that we get the normal magnetic field for a straight wire times some factor. And that's what I'm trying to emphasize. Why is this handy? That has the right units because it's a formula I already know. This has no units. We check the units. Is everybody cool with that? enough on that. What if there was some inner radius, right? If there was some inner radius, you'd get minus radius inner here squared and minus radius. Do you remember when we had stuff that looked like that all the time in Gauss's law? It just so happens that the inner radius happens to be 0 here. But when you see it this way, you're like, oh yeah, I remember these ugly messes. So it kind of.
Hey, Justin.
Yo.
Should it be little r cubed on that one because of the small r in the denominator, or am I missing something there?
No, no. Because look, this one here, when we divide through, is going to cancel one of those. So actually, that was the next line I was going to write. That's what it is. Do you agree?
Sorry, where does one of those cancel in the lower one?
This cancels that.
Yeah, and I mean when we did the integration, where would it have canceled?
Oh, okay. So when we do this integration, we're doing this. So are you open to this step?
Yep.
Right. Well, then when I plug in the 0 limit, it disappears. So I just get little r squared.
Oh, okay, gotcha.
Gotcha. And there's still the big R squared downstairs from this current density, I think is where that came from.
Okay, gotcha. Thanks.
Yeah. Okay. What do you think? These are our results. Feeling good on that? Well, what do we always do next? What's that? Okay, check the units. They work. I can tell that. So this is the way I check it. I know there's a mu naught on top, I on top, meters on bottom. Mu naught on top, I on top, equivalent to meters on bottom. Outstanding. What next? Are there any other ways to check this? Are there any other ways to check? Big R, are there any other ways to check this? Remember, if you plug in big R into both of these formulas, shouldn't they match? Because that's the border. If you plug in a big R here and you plug in a big R here, they match. Agreed? This would be 2 pi big R. This would be 2 pi big R, but you'd have one of them cancel. All right, so it works out. Okay, so that's where our two checks. Check the units and then check if it matches when you plug in big R into both, right? Or the check that the boundary condition makes the equations match. What did we do after that almost every time? I like this a lot. It's a word that starts with P. Oh, plot. These are like the worst hints ever. Oh well. Look, don't you have a look at the next page? Part G is hidden on the next page. You thought this stopped at part F. No, no, no. Plot it. We're plotting these things. Clean up just a little bit. Right? What's the special radius that matters a lot? Big R. So when little r equals big R, what is the vertical height? B. We just did this. If you plug in, right, so keep in mind here, this is what's confusing about this. Big R is a dimension of the wire. We can't change that. Little r, after you complete the math, you could go back and say, well, I could have chosen little r here, or little r here, or little r here. The idea is the little r value is free to vary afterwards. So if little r equals that value, what do you get? Just say it. You plug in little r equals big R, what do you get? Yeah, that's it. So that's how I get the, don't overthink it. It was just that. That's all I was trying to say. Does that make sense? The idea is if you plug in little r equals this number, I should get that number. That's all I'm trying to say. What if you plug in, what's another good number to plug in for little r? 0. What do you get when you plug in 0? Which of these equations is valid if little r equals 0? The top or the bottom? The bottom, agreed? 0 is less than, so if you plug in 0, what do you get? Hey, I like that. What's the shape of the graph? Linear, concave up, concave down. How do you know? Because it's r to the first power. So we say is proportional to r. To be clear, this is some, I'm just going to mention this really quickly. Alpha looks like this. Fish swimming left. See the subtle difference? Is proportional to, you get this little flattening of the fish tail or something. It's like so hard to tell these apart. That means is proportional to. How about I just write the word linear, because that's easier, right? Well, over here, it's, oh, I want to write fish, and then I could just flatten it out, right? It's proportional to 1 over r out here, right? What does that look like? Show me with your finger. Just trace it out in the sky. Yeah, it's going to fall down, right? Something like that. It's like slightly curvy. Hopefully that looks slightly curvy. Can't tell from up here. All right. Well, on your workbooks, we've got our wire here. What's the B field right at the center? 0, right? How about where is the B field maximum? At the surface, right? So what direction does the B field point? Which direction was the current? Do you remember? Okay, so current out of page. Right? So right at this point, what direction does the B field point? What way?
Up. Okay.
Yep, up. And that's going to be the biggest one. So draw that arrow pretty big on your notebook. If I go halfway towards the center, what should happen to the size of the B field? How far down should it go? If I go halfway to the center, and this is linear, it's half the size, right? And then I go all the way to the center. Now, what about these other points right here? What's different about this point? Same size, different direction. Same with this point and this point, right? We're not going to do every single point in the universe, but now there's a couple of dots out here. I'm going to number them just for communication. 2, 3, 4. Which of these dots, 1, 2, 3, or 4, has the same size as this arrow? I'm going to say it again, right? Remember, this is the maximum. This got cut in half. Which of these dots outside got cut in half?
1.
No. 2. Look at the equation. It's different, right? Inside, it's linear. Outside, it's 1 over, right? So think about it. We need to plug in. So right here, this is B equals mu naught I over 2 pi, and I'm just going to put in parentheses R. If I want to cut this in half, I need mu naught I over 2 pi 2R. Do you agree? That's this one. Take a look. This is R. So this is 2R. This is the one that gets cut in half. Did that make sense, Jacob?
Yeah. Thanks.
Yep. And so this is what I was trying to stress out of all this. It's a little bigger here, And then it starts falling off, agreed? But the point is, inside the field ramps up pretty quickly, then outside it falls off slowly. That's what I'm trying to show here. The field ramps up pretty quickly and then falls off kind of slowly. Kind of slowy? Oh man, the caps are going back on. That was just one weird adjective too much, right? Kind of slowy. At least I still got paid. All right. I don't know. Is that making some sense though? Yeah. Now, obviously, you could do these arrows everywhere, but all right. Gosh, is there a shortcut we could have used to do this problem? Well, let me make sure we got everything done. Yes. Yes. Okay, we got it all done. Do you remember any shortcuts that we did in Gauss's law to save us time for uniform? Yeah. Memorizing is not a bad option sometimes, right? I don't encourage memorization a lot, but for some of these, that is a good technique. Like, I sure hope you got mu naught I over 2 pi r memorized at this point, because we've been doing it every day for like 2 weeks. I need to erase this graph. Can I erase it? Okay. How are you feeling on this? Just give me a thumbs up, thumbs down, thumbs sideways. Okay. Did all the work in Gauss's law kind of help?
Yes. Yeah.
Is it helping you distinguish between the different radii and such?
Yeah, definitely.
All right. It's still not, we've only done one example here, but let me show you something else. I'm going to go back to our old Gauss's law comparison. So if uniform, there was a trick we used. We said Q in, how about I just write it like this? It was times something. You remember that? The Gauss over the total.
Yeah.
But what was maybe if I write this, remember that Q is oftentimes the integral of dq, which is equal to the integral of rho dV. So it was what over what?
Wasn't it the volume enclosed over the total volume?
Yeah, the volume of the Gaussian. Or yeah, so you had it right. Or sometimes we call that volume enclosed over volume total. Volume of the object. Remember that? What do you think the Amperian equivalent is? Yes. So let's get that up here. So if your current is uniformly distributed, we're going to get Bs is equal to mu naught, some constant. Notice the mu naught's on top, the epsilon naught's down low, so what? We're going to get what? Tell me what to write. I total. Yep.
Parentheses, A Ampere over A total.
Now we use areas, right? A Ampere. However you want to write it, over area total. And to be clear, keep in mind, I want to remind you where this comes from. It was from the fact that I is equal to the integral of J dA. I bring this up because this all hinges on J. What type of area did it use? Cross-sectional, right? So that means these need to be cross-sectional. So it's the cross-sectional area. But I mean, we're basically only doing cylinders here. So it's basically you're always going to get pi r squared, or you could have pi r outer squared minus pi r inner squared. You know what I mean? If you had so if you had something like this, wouldn't this be pi r outer squared minus pi r inner squared? The outer circle minus the inner circle. I have a question for you. All right, well, so this is good. Now let's make sure before I ask my question. Any questions about this? I'm a little concerned. I can erase this part here. I'm worried that there's something wrong about all this, and I want you to see if you can tell me if there's something I should be worried about or not. All right. Generally speaking, when you get closer to the wire, when you get closer to the current, the B field goes up, right? But wait, we just said inside, for some point inside, let's subtract the circle. We said that inside as you go to smaller and smaller values of R, the B field goes to 0. But you're getting closer and closer to the current. Is that a contradiction?
They're on the outside.
So what about this stuff on the outside?
The current.
So you're right. And so what he's saying, let me see if I can give you this right. He's saying this stuff doesn't matter. So you're enclosing less current.
Yeah.
But right, if I use the Biot-Savart law, this should contribute quite strongly, and so should this, but these should be weak, right? The point's closest. So that's what I'm worried about. It's a symmetry thing, right? The idea is if you're sitting right here, yes, you get a huge contribution from here, but all these other contributions tend to cancel it out. So you can view this as some kind of dividing line right here, right? And so if you're looking at the contributions to the wire, right? So there's some current flowing out of the page this way, some current flowing out of the page this way on all these other spots up here. And so there's a lot more spots with current, even though these produce a weaker contribution, there's more of them. So it tends to balance out, and that's what cancels the outside. I don't know, did that make any sense at all? I'm trying to say that basically a heuristic argument for why this stuff outside doesn't matter. You're absolutely right that it doesn't matter. And I'm saying that this part would balance out all of this. Even though this part is all farther away, it's going to balance out that part. And that's why we're basically canceling out some of the contributions. You're getting partial cancellation, even though you're closer. Cool? Yeah. All right, enough on that. Okay. Take a look at page 166 and page 167. There's a couple of worked solutions for you. Do you see it? They're in color in the solutions if you want them. Uniform, non-uniform, you got some shells. Just take some practice. Look at page 168 and 169. There's some homework for you can do. There's one with a uniform current density, shell. There's one with non-uniform current density, shell. There's some with some disgusting non-uniform current density. Great. There's one on page 169, 29.27. That one's got the shells and probably current runs one way and then one. So you can imagine an exam question that's going to be some amalgamation of this shit, right? So that's not too bad. You're going to get on your next test some kind of Ampere's law question. You know what's coming. It's going to be just like the Gauss's law. There's several variations I can mix up on you, but the advantage of Ampere's law over Gauss's is there's much fewer cases to try. It's like, this doesn't seem so bad at all compared to Gauss's. Should we take a break now? I'm cooked. Let's take a quick break. All right. Any questions from Zoomers before we take our break? I see a comment there. Check the chat. Oh, whoops, that's Jacob. So I'm gonna guess that's a no, Jacob.
Yeah, I thought you responded to that earlier, but it's all.
Oh, did I? Maybe I just didn't click the button that said I did. Sorry about that. All right. At the end of class or in class tomorrow, we can go over grades if you guys want. Let me see if I can do this without screwing it up. So I'm trying to, those of you on Zoom, I'm trying to direct message you your exam score. Okay. I won't always do this, but. Jose. Oh, Jose, did you already pick yours up? I got it. Oh, you already got his. Okay. You can tell him his score.
Yeah, you showed me. Thanks.
Yep. Let me give Michael. Who else we got out there? Wilfredo. Okay. I think I got it. You guys can get those from me in lab tomorrow, but at least now you kind of know your number and you can look over the stuff online that I sent out or whatever. Yep. Oh, yeah, for sure. We can do the labs tomorrow in class if you want. And I need to take a break, but at the end, I do have the grades printed out. So if you want to see like a grade check, we can do that. But I'm going to take a quick break. I gotta relax for a minute. So just leave those there. I promise to show them, or we get too busy, or if you got to take off right after, I'll show it to you in lab tomorrow. So.
Yeah, well, I'm gonna talk about that. I'm just like, we're not get like the you gotta do if somebody is going or physics. The exam, I mean, we just take this last time. Yeah, take that. Well, I would be nice to know that, like, since this one is slightly high, slightly low. I got like 50. It wasn't great. Yeah. Yeah. It's like, I'm busting my ass and I'm doing a lot of shit, you know. Keep it going. This one.
I know that at one point in class, this is the one where the normal series apply. It looks like series, but we gotta use parallels. So you can't use the equivalent facets of that. Yeah, and I mean, it's kind of like, it just turns out to not work at all. So I didn't rewrite the solution. Look at 29. Like, yeah, and it's like straight out of the volume. It's upside down. So it's the other way, which I just realized. Well, all I can say is, I know the typical problems that I'm trying to ensure. All I can say, right? So, and I'm keeping track, and I've got my notes of what all I can do. So, I do feel like, although, sometimes what I feel is a sophomore, I honestly thought the two first passes was a sophomore. I mean, you're going to pass, right? And still, the next test, like you built up something small.
Yeah, I was trying to relate. So I was asking for it. Yeah,
so it's like if I don't kind of play the game, it's just down the road. Like, would that be the job? Yeah.
Yeah, I give you one. Yeah. The only one that you got almost fully or 7. It's out. I mean, 7 I should have got. Yeah, it's a change. Yeah. It's like this, right? But you know, other than this, it's actually been not terrible. Yeah, right. It's good. What is that like? Yeah. Like when I used to teach it. Yeah, I need to stick back. Like last Thursday night, last that went straight to trade. Drinking beer all night. So, oh God, be out of the lab. No, actually watching talks is so yeah, that's good. Sit back in the car. It's like super easy. Like compare that to grading, right? Grading reports, no 8 grams worth of grading reports. Grading reports. Well, let's do that. Yeah, I'm gonna do that. Yeah, I don't know. It's this semester. I just barely set tense. Well, because I've got to stay on top. I try to. A lot of this no, I just get there. What I do is I type up the solutions in advance. So they're like super detailed. All I had to do is my card didn't choose lock. Yes. It shows up. Well, sometimes no. Oh. I know what I was trying to get at is that make that like yeah. Oh yeah. Well, the ego was yeah. Yeah, it's true. It is. What it is, it's yeah, much better of a relationship that's like that. So yeah. That's nice out. Not cold for a while. It's one of the few nights where we're actually in.
So yeah, we're on pace for once. So all right. Let's see here. Okay, sorry if I took too long there for the break. I know I need to make a note on something here. Okay, let's pick up on page 170, solenoids. All right, and if you could have your book laid out flat. Am I on here? Yeah, okay. So you can see page 171 and 170, all of that. All right. So if it helps, got some solenoids here. Here's a solenoid. It's just a wire wrapped around in circles. Got it? So wind the wire. Now this particular one happens to be called a doubly wound solenoid. It's wound all the way down and then all the way back up. So you can see both the wires spit out here at the top. All right. And I think I actually have a singly wound here somewhere. So here's some other solenoids, right? All of these are solenoids. This one is singly wound, right? It comes in one end and spits out the other. So, right, this is the difference between a doubly wound and a singly wound. The doubly wound, both wires come out at the same end. The singly wound, one comes out at the top. I'm trying to draw pictures of that. You see that on page 171? Yeah. Okay. So in this case, I'm going to take a little bit of latitude here, and I don't want you to take any notes. I want you to listen for a minute, all right? I'm going to be looking at the figure that's at the bottom of page 170. And I want you to imagine you take one of these solenoids and just cut it in half, right? You could see like there'd be a bunch of current going into the page on one side. And there'd be a bunch of current out of the page and into the page on the other side. So this is supposed to be like one of the loops in the next loop. Is that kind of making sense visually what I'm trying to draw here? Let me just get this done. Something like that. I think that's approximately right. So again, that's just one of these things, and it's the current going into the page on one side, out of the page on the other. Now in this case, I'm going to draw an Amperian loop. Okay. Now in this case, I want to think about the magnetic field. Outside of this, right? Outside of these things, I'm going to make a claim. Actually, maybe I'll draw another Amperian loop here. So I can't really draw this, but that's supposed to be like, oops, here. You guys see that? All right. Okay, right. Imagine I do an Amperian loop all the way outside of this thing. Right? How much current is going through that loop? It's going around in circles inside of it, right? So keep in mind, let me show these. If I have a doubly wound solenoid like this, the current that goes through the loop is actually related to these two wires. That's the current that goes through the loop, right? If my fingers are the loop here, should have brought a hula hoop, whatever. Right? That's my loop, right? Well, there's current that goes down and up. What's the net current going through the loop? 0. How about right here? There's some that goes down, spiraling down, but then there's some that comes spiraling up. How much current is enclosed that goes through the loop? 0. So you just told me for the green loop is the length 0? No, that's 2 pi r. So what must equal 0? B field. Is anybody who's doing the solenoid lab in here? You are? So what should be the B field outside of a solenoid? 0. If it's doubly wound and you have as much current helixing down as helixing up. Does that make sense? Strictly speaking, if you have this singly wound one, it might be different. We'll discuss that in a minute. All right. So, okay. You agree the B field is 0 out here? All right. Now, what about the direction of the B field? How about right here? Let's say, what is the direction? How about right here? What's the direction of the B field? Well, let's start with one of these wires. Pretend this wire is infinitely long. Even though it's not, it's a coil. But if it was infinitely long, what direction would the B field be here? Down. Now wait, what if we had a contribution from this wire? Wouldn't it be a little bit smaller? But what about this wire? So it's almost as if, when we're looking at points here, all the contributions from these, there's, right, if we're somewhere near the middle of the solenoid, maybe not, this isn't necessarily valid at the end, but if we're somewhere near the middle here, we expect the B field is going to basically point for this particular one straight down, right? Well, think about it. Grab that coil. Which way does my thumb point? If I grab that coil, it points down. Right? Okay. So the B field here. Now wait, what about from the straight wire? Would they contribute a different way? What about here? Still down, do you agree? Line up my thumb. So notice, right, it's a little bit different because these ones are to the right of an X. These ones are to the left of a dot. They both contribute down. So everything's down. Okay, right? Huh. I'm gonna try something fun. I'm gonna try Ampere's law in its full vector form. Well, I need to go, this circle on the integral simply means go all the way around the loop. Are you okay with that? It just means on a closed loop, means make sure you go all the way around. Well, I need a BDS here, BDS here, BDS here, and BDS here. What's the integral of BDS right here? Let's pick the easy one. If B is 0, 0. So do you agree this part of the wire has no contribution? And let's just assume we're going this way around the loop. What's B dot ds right here? Okay, wait, let's go back. Dot products and cross products. Dot products pick off things that are what? Parallel or perpendicular?
Perpendicular.
Dots are parallel. Cross is perpendicular. Okay. Let me put it this way. What do you get when you cross a grape with a rhinoceros? Oh, wait, no, I did cross products. Sorry, I was going into my jokes. Let's not do this. Let's just write our vectors. A dot B equals what? AB cosine theta. A cross B has magnitude AB sine theta. Agreed? All right. So what do you get when you do the dot product? What angle is it? 90. So if they're perpendicular, the dot product is 0. Agreed? Now, why are we doing this? Well, here, I don't need to worry about it because B is 0. Here, I don't need to worry about it because they're perpendicular. There's only one segment that's going to contribute right here. Do you agree? So I'm going to get B times the length of that side, whatever it is. Let's just say this side has length L, is equal to mu naught. How much current is enclosed? No, not all of it. All of it would be all of it. Each one of these has a current I. So do you agree it's 3I? Or maybe more general? How about we just call it N some number times I? Are you okay with that? And check this out. This can be rewritten. This is the field inside of a solenoid, approximately. Now, those of you giving the talk on solenoids know there's also that formula that goes that's different than it. This tells you the value far from the ends. So remember that when we did parallel plates, we ignored the fields at the edges. We call those the fringing fields. Here, we're ignoring the country. This is only valid when this kind of symmetry rules, right? When you get close to the end, well, then you don't have points above to cancel out the ones below, and it doesn't quite work. So this is valid somewhere in the middle, right? But we see the B field of a solenoid is mu naught N over L times I. This thing here is sometimes given the symbol N, lowercase. It's called turns per unit length. Now, I just wish there was a way we could have somebody give a talk and explain these different shapes. So we'll be doing that in lab. So we're going to revisit this in lab and we'll discuss the differences here. And I don't want to kind of steal Jesse's group's thunder here. So I'm going to let them discuss these. But this will give you something to look at. To be honest, we're never going to use any of this again, except for this. This is on your equation sheet, I think, or at least this one is. I forget. Let's double check. What's on there? Look for it. Yeah, there it is. Okay. So to be clear, though, n is the number of turns, and little n is the number of turns per unit length. And so just so you agree, if these both have 100 turns, right? I think these both have 100 turns. In this case, do you agree there's a different number of turns per unit length? Right? This one has twice as many turns per unit length. So hopefully that's a stronger B field. We'll see if that's true. All right. Good enough on that. How do we use this? Solenoids are super practical devices, right? Now, do it like this. Here's an example of a solenoid. These ones are called air core. Right, there's nothing inside of them. Here's one. This has just got an iron core. And the idea is the iron inside, I'll pass this around. If you look, you can go to the hardware store and buy this stuff. It's called piano wire. Sometimes if in old school, you go to like Ace Hardware or something and want to get some of these. The iron inside can actually multiply this constant mu naught, sort of like the dielectric constant did. So remember, dielectrics could increase capacitance. Iron can increase this magnetic constant by a factor of 5,000, depending on the iron, 200 to 5,000, whatever. But so you can actually get, if you take a solenoid here, and you have a lot of turns per unit length, like this one does, wrap it really tight, and then you put in an iron core like this, you can actually get a huge field because you get these two multiplicative factors times our normal currents. So you can take 1 or 2 amps and get a huge magnetic field this way. If you're curious, I'll pass this one around. Here's another weird little thing. This is a relay. I'm going to try and draw this. I'm just going to pass it. I just think it's neat to see some real objects. I'm going to pass it around. Here you go. A relay. I don't know. I know this is basically solenoids are used in real devices. So that's why I think it's important to see this and understand this equation. On occasion, you might get a word problem in the test or something where I ask you to say, hey, there's solenoids here, and that's producing B external. So this will probably be showing up in other problems as the B external. That's where it shows up. Okay. Now, imagine you take a switch here and a battery like this. And that little weird clear plastic box has something inside of there that looks a little bit like this, except it's enshrouded in white plastic. So inside of there, there's a little thing in white plastic. But the idea is, this is a solenoid. You could put an iron core in there. Okay, so this could be some iron. And then near that, you could have a long piece of metal. This is very simplified here. And let's just say this piece of metal is a cantilever. Right? So think of like a diving board, right? Well, if this material can be magnetized, the idea is you can throw this switch and cause this to connect something, right? And perhaps you could use this to connect another circuit. And the idea is the battery could be, over in Lompoc, and this switch could be attached to a launching mechanism for a nuclear missile. And so you could use this relay to do switching at a distance, right? This is pretty cool. You can flip a switch somewhere, and then the current can run over to a solenoid somewhere else and cause a switch to close somewhere else and activate some kind of other circuit. remote switching. I don't know. Anyways, I hope that makes sense. You can imagine this click, you get a magnetic field and cause this to move up or down and connect a circuit. That's what I'm trying to pass around there. If that looks cool, great. That particular one, I believe, is a DP-DT, double pole, double throw. So if you know anything about switches, and I hope I'm not screwing this up, I'm not an expert on switches, right? Remember when we had these switches where you could have a switch that could go to position A or B? It could be thrown two ways. It's a double throw. But this is just one pole, right? So that one has two switches that could go either to position A or position B. And so different types of circuits, you might need different types of switching. I think that's enough. So good on that. It's pretty cool. There's applications. That's it. Look at the bottom of page 171. Toroids. Here, have a toroid. Right? Pass those around and look at them. I got to get them back eventually. Thank you. So, yeah, that's fine. That's good. So these toroids, they're basically a small, a lot of times these are used in radio circuits, but imagine you had a donut, right? It kind of looked like this. It's hard to draw. Right? So imagine you have some piece of iron like this that's a donut. Again, we want to use something that's easily magnetizable. And the idea is you could try and wrap the wires around these. Sorry if my picture's not very good here. Thank you. Whatever. But the idea is you have these loops of current going around here. That looks terrible. That'd be nuts. But you saw what it's supposed to look like. It's supposed to look like this. And you can't see this at all on Zoom, no matter how much I move in. So but you can see it in the lab tomorrow. All right. Now, this one is discussed in your work, in your textbook usually. And I'll be honest with you, most physics classes your teachers teach solenoids and toroids, and I just got to give up on something, and this is what I'm giving up on. I'm not going to explain toroids to you, but you can read the formula in your workbook, I think, or in your textbook. So if you want to learn more about this, it's a very practical application. So if you're into radio circuits or something, you know, yeah, check it out. These are used, the toroidal geometry is used in like a tokamak fusion reactor at the Princeton Plasma Physics Lab or whatever. So there are applications of these, enough said. But check it out, read it, skim over it in the book. It's not on the test. Solenoids, the formula might be used on the test. That's about it. Good on those? Okay. Oh, go ahead.
So the solenoid, it creates a very strong magnetic field.
Yes.
Just downward. Or
well, it
whichever
depends.
one.
If I float in this one, it's kind of hard to see. Do you agree? I can't tell where's the front and the back.
Right.
It depends on how it's wound. If current's going this way, B field's up.
Right.
If current's going the other way, B field's down. It's the same as grab that coil. One of your favorites, a right-hand rule. You curl your fingers in the direction current flows, and your thumb points in the direction of the B field inside.
Right.
So what's cool about these is the B field's either going to be this way or that way. So solenoids have a very strong B field either into or out of the page, so to speak. Is that good?
Is that like the most optimal way of getting like a super strong current?
So there's a couple of different things we could do. Right? So basically, this is a way you could get a massive magnetic field for a small amount of current. So is this, if you fill it up with an iron core. The other thing that's great about this, okay, so let's talk like practical lab physics. Not that this is a big deal, but I'm kind of excited about it. So if you want a constant E field, what did we use? Parallel plates, right? Remember that? We could get a constant and there'd be a plus and a minus plate, and the electric field would point down in between these two particular ones, right?
Yeah.
And then it would get kind of confusing at the edges, but we ignore the edges. Well, if you want a constant B field, we could see one way to do it is a solenoid. Did you notice it's a constant? Constant, constant, constant. I could be a constant. Now you could make it vary. Here's an example. You could plug this into the wall socket, and then this current would go back and forth and back and forth, right? So that, right? But assuming the current is connected to a battery, you can make this constant. This is a strong constant B field, right? And this would point basically that way, if the current is flowing this way, right? Right? The other way you could do it is what? What's your lab on?
I have Helmholtz. Oh.
Helmholtz coils. Very good.
Get the uniform. The uniform.
So we haven't talked about this,
Yeah.
but we've seen it in lecture a little bit. Imagine you take two coils like this, and so this is supposed to be the coil here, this is supposed to be the coil here, and there's some certain spacings that we'll leave for your talk, but there's a certain special gap here, and there's a certain size of these. So let's say this has some radius and this has some gap between them, D. When D is some certain special value that I bet his talk will discuss next Thursday, you can actually get a constant B field inside too. And there's a, so you're coding it?
Yeah.
And a different group, who's measuring it? Is that anybody in your class? Okay, that's the other class. The other class is actually measuring it. So if you want to see the actual data, I'll get the other group in contact with you and I'll try and do that. If you can get to the lab like 15 minutes early tomorrow or something, or whatever. We'll worry about it later for sure. Or I could just get their emails or something. But yeah, so we actually have two ways to get a constant B field. Yeah, all right. Why is this useful? Can anybody think of a solenoid that has applications that's used pretty much every day in America, all over the place, in every town that has a hospital? MRI. MRI. You slide human beings inside a giant solenoid. That puts them in a B field. That causes their nuclear magnetic moments to align with the external field because mu dot B negative is the energy. So you slide a human being inside of here. Oh, there we go. I can slide my, and now my arm would be exposed to a constant magnetic field inside. And so all the magnetic moments from all my molecules would tend to align to that. Then you can send in radio signals and interpret the radio signals that come out, and you can learn about that. We'll discuss that later. All right. One more. We're almost there. What time is it? 6:30? Yeah. All right. So next we're going to talk about magnetic flux. Okay, I'm going to call this good on this stuff. I think it's interesting. There's not much we can test you on this, but it's super applicable to real life. Enough said. Let's focus on stuff that will be on the test for a little while. Go to page 161 while I erase the board and kind of read that. Page 161, or just after problem 29.20. This is probably my favorite subject in the entire course. I just think it's super fun. And it's not that mathy. It's an interesting subject. It looks mathy at first, but it's not too bad. Okay. Let me put some color up here. Yes, that's better blue marker. Oh, it's still crappy. Damn it. All right. What is magnetic flux? It's this integral. All right. Now, I want you to think about this. Let's say we have a bar magnet here. All right. Actually, I'm going to switch the poles just to make it easier for me to draw. Okay. Sorry about that. What direction does the magnetic field go near a north pole of the magnet? Out or in? You're going to see me draw this picture a lot. Does that kind of look like an electric dipole? Right? Out of the plus charge into the minus. If we could look inside the magnet, they would all continue to flow that way. So this is just like a loop of wire too. If you run current through a loop of wire like this, if you take this loop of wire and run current through it, the B fields are going to swirl. Remember we saw that with the iron filings, the little thing that I brought out here, and I was shaking that. Now, let's say I have a loop. Right now, it could just be an imaginary loop here, but you could have it be a loop of wire, right? We might expect some of the B field goes through the loop. I want you to think of magnetic flux as amount of mag field lines that go through the loop. I want you to think of it as amount of field going through the loop. Now, obviously, I didn't draw all the lines here. Maybe there's another one here, right? Maybe one right here. And now if I draw those lines on one side, I feel it's only appropriate to draw them on the other to keep the magnetic field density uniformity. Whatever. All right. So the idea is, notice this one in the middle is pretty much perpendicular to the area of the loop. But these ones on the top and the bottom are not, right? Oops. There's some curviness there. The idea here is sometimes the magnetic field is warped. And so sometimes there's an angle between the magnetic field and the area vector. So far, so good? So in this example, if I was trying to describe this mathematically, that's supposed to be out of the page. Sorry, I can't draw it very well. So, sorry, my angle's like backwards from this picture too, whatever. But do you agree that the area here is in the I hat? So it's a small amount of area like this. And this area might be something like dx, dy in the I hat. If you did multivariate calculus, you know what I'm talking about? So if we were doing the right flux integral, we might really want to understand multivariate calculus. I don't want to explain this, but you can kind of imagine this could be done, right? We're going to generally restrict ourselves to some easier cases where the angle doesn't change. And that way it's a little bit easier. So basically we could rewrite this one in a large number of cases is going to be B times cosine of some angle times some D area vector like this. The idea is we're going to hopefully restrict ourselves to cases where the cosine theta term is just pops right out. Got it? And so oftentimes this is going to become, not always, but often it will become cosine theta. How about I just say it will often be approximated by this formula here, BA cosine theta. Good? All right. Yes. Questions? The red could be like a coil. So if I brought a magnet near this coil, right, I could talk about the area of the coil and the B field through the coil. Yep. Is that good? Yeah. All right. Before we do anything with this, let's go to the next page, 29.21. 29.21. Let's see what we can get out of this. All right. I think it's crucial that we get an understanding conceptually, not math based. All right. So I spent a lot of time on that, but let's Let's see if any of that sunk in with an example problem, okay? 29.21. We're going to get there. We have a long straight wire here. Current is flowing upwards. There's a loop, rectangular. A little bit taller than it is wide. Okay. There's my rectangular loop. What direction is the B field at the plane of this loop? Into or out of? Grab that wire. What's going to happen to the B field as I go to the right? Okay. So now in this case, this is going to have some magnetic flux. Do you agree? What's going to happen if I turn the book sideways? Would I have more or less flux or the same? I have the same amount of area if I turn the book sideways. Agreed? Do I have the same amount of magnetic flux? Less, because there's less magnetic field going through the loop. Agreed? Right. So even though the area is the same, we get less flux. What if I do this scenario? What if I turn the book this way? See what I'm saying? If I turn it this way, am I going to get more or less flux? A lot less. Right? Think about it. The B field right here is going parallel. How much of it is going through the book? Right? Almost none. Now you could say, wait, some of it's curling through there, but keep in mind, try to watch this if you can. Right? If I'm curling my fingers, some of it's going to go into the book this way, but then some of it's going to come out of the book this way. It's actually zero flux. Right? So when I put it like this, there's some that goes this way and then some that goes that way, and it cancels out. So the point of this was to show, depending on which way you orient your loop relative to a magnet, you could get a lot of flux or no flux. Agreed? Huh, interesting. I'm going to write up something that I think is super, super interesting. Why do we care? You're tired, you want to go home. The claim is this is fundamental to the existence of life on Earth at this point. I argue it is because of this equation. How would I say it this way? You probably know that letter is script E, right? We're going to talk about this later. You don't need to take any notes right now. I'm going to write this down. Another way. We're going to do this next time, okay? My claim is you can get what's called induced voltage. It's minus n times the time derivative of, what did we say was our approximate formula for magnetic flux? B A cosine theta. My claim is this. I can create electricity if I change some of this. Do you see how huge that is? Think about this. With the exception of solar power, all electrical power generation on Earth pretty much uses this. Nuclear power, coal-fired, natural gas, whatever. How does this work? I want electricity. Give me some ways I could create electricity. I've got a loop of wire with an area. Tell me something I could do. Let's say I have a magnet here. What's something I can do to get electricity? What's that? Move the magnet. Do you agree that would be changing the B field? Give me another way. Rotate it. Isn't that changing the angle? That's how most power generation works. You put big magnets and you have them spin, and they go past the loops and you generate electricity. What's the other way? Could you change the area? Could you imagine wrapping a wire around your chest many, many times, and as you sleep through the night in a solenoid with a constant B field, you breathe and your lungs expand and contract, stretching the area of the loop, and you could record your sleep apnea? This is a technique you can use if you have really bad sleep apnea, I guess. They wrap a coil of wire around your chest, make you sleep in a magnetic field and record the voltage, and you can register somebody's sleep patterns over the night with an electric signal. Look it up, see if I'm full of it. It almost sounds too good to be true. It's almost like this equation could solve all the world's problems. What if you like basketball? What if, mind you, you really like basketball? You can see the NBA right here. But that's not all, folks. That is not all. What's a common way we talk about angles? Give me an angular kinematics equation. Okay, give me a delta x equation. Yeah, that's a. Do you agree? Give me the angular equivalent. What if alpha is equal to 0? What do you get when you take the derivative? Negative sign, chain rule, an omega pops out. You get the more basketball. I'm telling you, man. We got a lot of basketball to cover next week. Right? Think about this. If you have the strength of the magnet, the area of the loop, the number of turns, and the rotation rate, you can get 60 hertz power, right? This sine wave, that's, I guess it doesn't work when you, yeah. That's the electricity out of the wall. Isn't that crazy? I'm telling you, isn't this spicy? Hold on. Let's show you a demo here, all right? I know we're kind of getting ahead of ourselves. This is why we care about magnetic flux. That first stuff was pretty boring, right? Let me see if I could show you this. I think there's a way to do it. You guys could start packing up if you want. I'm going to show you this demo, though, so I think you'll appreciate the demo. Oh, shoot. Did I take the batteries out of this? I put some other ones back. Come on, please. Don't fail me now. All right, thanks. Oh, I can't. Yeah, but I think I got it. I can do a share screen. Oh my gosh. Okay. Oops. And so let me see if I could share screen. One. And I think, will you guys also see that? Yes. All right, and I think they're looking at it. Zoomers, are you looking at something loading the FET?
Yep.
Yeah.
Okay. Oh my gosh, come on now. This was the first comment. As you wiggle the magnet, you see electricity flow. Okay, transformers. You could imagine if I put these two coils right next to each other, two air core solenoids right next to each other, I don't see any induced current. But if I change this, there's now a changing flux. You see it? And the faster I change it, the more omega I get. Whoops. I can get more electricity if it changes more rapidly. This is what we just saw. The omega matters. And now let's go. Right? The idea here is if you can make the magnet rotate at some angle, you generate electricity. Now, that's basically the concept that we just discussed with the women's MBA right there. Okay, we're going to come back to this next time, but I thought you might find that slightly interesting. The concept behind here is how do we get AC power? So what are we going to do in the last part of the semester? We're going to talk about how you generate AC power and then do math on AC circuits. And to do that, we need to learn about something called inductance, which is the solenoid equivalent of capacitance, right? It's some property of a circuit. So we'll pick it up there next time. I think that's enough. If you didn't get your test, pick it up. If you want to get your, all right, good night. It's just sometimes you get tired.